In addition to knowing the basic properties of ionic compounds and, kind of what things to look for to recognize if a compound is ionic, you are going to have to explain why certain properties of ionic compounds exist. And the most common one is going to be to explain either the melting point of an ionic compound or discuss something called the lattice energy for an ionic compound. And so that's what we're going to be talking about today. So melting point hopefully makes sense to you. Melting point is the point where you're adding enough energy to a solid sample of your ionic compound, and you have added enough energy to your ionic compound for your really organized lattice structure to kind of fall apart. The temperature that occurs at is called its melting point. And with this property that we're going to kind of talk about, it will help explain the actual temperature. In this case, it's going to be in degrees Celsius that melting point occurs at. But another thing that you could potentially be asked about is something called the lattice energy. And the lattice energy is the energy that's given off when oppositely charged ions in the gas phase come together to form a solid. It is a pretty specific thing, but the magnitude of the lattice energy gives us some hints about some of the things going on inside your ionic compound. So what you have to think about is that if I have to take molecules, or not even molecules, if I take atoms of different elements and I heat them up to the point where they are a gas and then turn them into ions, I add lots of energy to make that happen. So I have pumped in lots of energy from a heat source or electricity or something like that to turn them into their ions. And we're going to come back to our good old friend NaCl. That means that I have Na positive, the Na cation in its gas form, and the chloride ion Cl minus in its gas form. So I've got these ions heated up. I've got them ionized to the point where they have their charges and they are high in energy. And so what ends up happening is if I bring them together, and you can kind of see in the picture here, I have a cluster of these atoms. If I bring those things together, they will form that very organized crystal lattice that we talked about before in the form of NaCl solid. So we've got that nice repeating Na plus next to a Cl minus, next to an Na plus, and it goes on and on and on. When that happens and those ions turn into that solid form, your elements stabilize. And when that happens, they lose some of their energy out into the area around it, in what we call its surroundings. And the magnitude of that change tells us kind of basically how much energy those particles had and how much energy they release once that stabilizing structure is formed. And that value is called the lattice energy. So in the case of sodium chloride, its lattice energy is negative 787.3 kilojoules per mole. So that means when I form a mole of sodium chloride and all of my crystal lattice comes together, and by the way, a mole of sodium chloride isn't that much. It's making like 58, 59 grams of salt, so it's not that much. When that lattice forms, it releases 787.3 kilojoules when that happens. So what that means is my high energy ions in now this organized, very formal crystal lattice are much more stable to the tune of, 1,000 kilojoules release, which is a lot of energy to make that. The lattice energy, what it tells us is essentially an estimated strength of the attraction of a bond in an ionic compound. So what I mean by that is if I see a substance that has a very negative, so large in magnitude, negative lattice energy, what that tells me is that when those ions get together in that very organized lattice, they have very strong attractions to each other, which leads to them releasing a lot of energy. They're very stable then. And so if I have a strong crystal lattice, it makes things a little bit more difficult when I want to try and break those things apart. And so if I have very large magnitude negative lattice energies, it lets me know that the bonds that are attracting my two ions together are very strong. Okay? So like I said, the larger the value, the larger or the stronger the ionic attraction is. Now, these values translate or can be kind of roughly predicted using something called Coulomb's law. Now, Coulomb is a measurement of charge, but it's named after a person with the last name Coulomb. And what ends up happening is that when we talk about the Coulomb's law, there is an energy that represents the interaction between the pair of ions, so the positive ion and the negative ion. And there are kind of two factors that play into it. The law itself looks like this. It's that the energy that's represented between that chemical attraction is equal to this energy term value here. Now, this is not super important. We don't care so much about that. What we really care about is this part here, and we'll see that in just a second. It's Q1 times Q2 over R squared. Now, Q represents the charge of an ion. Usually, I write the positive ion first, and then the negative ion's charge second, and then R is the distance between the two nuclei. So if you think about in a bond, here's one nucleus, here's another nucleus. R is the distance between those two things, which is essentially what we call a bond length. So it's how far is the spacing between those two nuclei. When we talk about Coulomb's law, what we're really specifically talking about is this part here. So in any argument, I have never seen the College Board ask you to actually do a calculation with Coulomb's law, but they want you to kind of refer back to this concept here. And the idea is that if I take my charges and divide them by the distance between the nuclei, it can give me kind of an apples to apples comparison of what two different substances are going to behave like if I compare one ionic compound to another ionic compound. Like I said, I've never seen them do any math with it, but what I have seen them do is ask you to do a conceptual explanation of how it works. And so what I'm going to do is kind of go over a couple examples with you in just in the next video. The two big takeaways when we talk about Coulomb's law is that most of the time they are going to be talking about things that have different charges with their ions. So we'll compare something with one charge and another compound with another charge, or we will compare two things that have similar charge and then different distances for the bond length. And the way that it works in general is that the greater the charges of the ion, the stronger the forces are, and the shorter the bond length, the stronger the forces are. Greater charges mean that I have a larger positive or negative charge, and the bigger the difference in charges are, the stronger the attraction is going to be. As far as bond length, we'll get into the actual math, but if we talk about two things that are very close together, their attraction and interaction is stronger than if we have two elements that are larger and then have to be stuck together. So you get a more beneficial attraction when you have two atoms that can come closer together. I'm going to go through two examples in the example video, and I'll show you some models to kind of help represent that as well. So the first example is going to be number one. Why does MgO have a melting point of 2,852 degrees Celsius versus NaF, which has a melting point of 993 degrees Celsius? And the second one is, which compound, NaCl or NaI, would have a higher lattice energy, and explain. So I'm going to go over those two examples in the next video to show you how a Coulomb's law or an ionic compound problem is going to be answered by this. Like I said, it's not going to be math. It's going to be more of a conceptual idea of this Coulomb's law, and then we will check over those answers and give you a chance to try and figure out your homework. Okay, so make sure that you watch the next video because I'm gonna explain how to answer Coulomb's law questions. Good luck.